Okay, so today we're going to discuss a little bit something a little bit different as far as how we use probability to create something that we call normal distribution. And so kind of the topic of what we're going to do today is what we call normal distribution. So we have looked at before standard deviation, and we're going to look at how that plays a part in things that we expect to happen and things that we don't expect to happen, and how these things should all unfold. And so one of the first things that we're going to look at is we're going to look at a particular scenario to kind of get an idea of something that we refer to as theoretical probabilities. So everything has this idea of being theoretical, that under certain perfect scenarios that something should always work out the same way. So imagine the scenario that you take 10 coins and you flip them 1,024 times. What's the likelihood that a heads will show up out of those coins? So you really have only the two options, is you have heads and you have tails. And so if you look at this table here, it documents each one of the different scenarios that could potentially happen, where none of them are heads or all of them are heads. And we have this idea that these things are equally likely as happening, that the majority of what you're going to have is, if you look at what we call frequency, is the amount that something happens. You can see that 4, 5, and 6 are the most frequent of what we would think would actually happen, that you would get this even mix of heads and tails, and it's not that they'd all be one or all be the other. And so what we can look at is, first of all, you have your theoretical probability. So for 0 heads, you have a 1 out of 1,024 chance, and we're going to convert these to percentages. But if you look at these, what we've created is kind of what you've learned before about probability, is that you always write things as fractions. So the amount of times that something could happen out of the total possible outcomes. So if you notice, the denominator in each one of these are the same. So when we look at this, we're just going to convert these all to decimals, and you can do this on your calculator by yourself too as well. But the idea is, as we list these, here are the percent likelihood of each one of these things to happen. And so as you can see from these probabilities, the idea here is that you have 0 heads, which shows up 0.098%. So pretty much never would you see something like that happen. However, we should expect it at least to happen one time. We're never going to rule out that something could never happen, because you have 10 coins. It potentially could happen at some point. And the same thing on the other side, where you have 10. And if you look at kind of the shape of kind of how these are kind of spread out from each other, is that you start to see that they're symmetrical. So, having just a couple heads versus having a lot of heads is just the same likelihood. And then when you look at the middle, and you kind of add these things together right here, so you look at 20, 24, 20, that's about 60% of the time that you're going to get something in this neighborhood. And if you look at the frequency, how many times this actually showed up, you can see that that is the bulk of the 1,024 times that we've done this. And so when we look at sum of probabilities, one of the things that you learned in years past is that the sum of probability is always going to be 100%. You're going to have 1,024 chances out of 1,024 chances. So that the idea is that everything is preserved. There's none of these situations that will ever not happen. You'll always have something to be accounted for, or something that you'll know. And so kind of answering some of these questions, the observations that we can make about this data in this table is that there's symmetry around 5. Now the idea is that 5, it's split 50-50 as far as how many tails, how many heads, but that only happens 24% of the time. So even though we think of that's what should happen the most, the idea is that we can just kind of categorize that we're likely to see between, and this is kind of where we pick up standard deviation, 4 and 6 heads on the coin, as far as if we throw all 10 of them at once simultaneously, that at some way we're going to have between 4 and 6. That's the most likely thing to happen. And so, but if you really kind of look at the nature and how those things happen, this is what we call theoretical probability. You should have the same chance of getting no heads as the same chance as getting 10, because the idea is that the kind of the method that would have to go along with that, the kind of the idea of getting that all of them being the same would be a kind of a rare occurrence. And so the best way that we can kind of describe how these things happen is by using what we kind of already understand as being a histogram. So using that information that we have from our table that's on that same paper is that we're going to take this information and look at how it's kind of set up, look at how it's what the word that we're going to be using today is distributed. How are these things different? How are they the same? What does it look like? What does the table look like? Because when we showed our family information, when we looked at um, and when we've looked at some of the other data, we kind of used a histogram, but not necessarily with bars, which was what we're going to do now, but with x's. But you can keep those bars together, or keep those x's together with bars. So we're going to fill in this histogram by using these bars to show the probability, and we're going to use the fraction that we had. So if you notice here at the top we have 252. Now we're going to kind of fill this out and kind of go half of that, which half would give us our 126. You kind of cut that in half. Then you get 63 out of 1024, and you kind of go halfway in between there, and you would get 189. So that kind of gives us a guide of where these things will be located. We're not looking for perfection in any way. We're just looking to kind of characterize this. So what we can do with a histogram is we can label these so that we don't necessarily have to be all that precise. So the first one is 1 out of 1024. The second one, and I'm going to start using kind of just shorthand here. So this is 10 for 1. And as we saw in our table, we did have some symmetry there, so we can kind of copy some of this over. So we just need to add a 10 here because that for some reason was missing. And so we have 10, we have a little bar there. Notice that these are all connected side by side, so 9 is going to be 10, so we can kind of estimate what that is. So this is 1, this is 10, and then we can look back at our table and then we can see kind of what we were using before. So the next value was 45, so I'm going to kind of estimate where 45 would be. So that was for 2 heads, and that would also be the same for 8. That would be at 45. 7 was roughly 120, so we'll kind of go where 120 is. We have our guide of 126 as kind of a helper there, and so this is also 120. And then 4 and 6 should have the same value, but if we look at what that value was, that value was 210, so that we're kind of in somewhere, I would say, in this general vicinity right here. We can kind of copy that over, and that would be 210. And then our top value was 252. So if you look at this, you can see that there's obvious symmetry of these kind of values, so that you have the same number on one side as you do the other, that having the majority of our data, as we've looked at before, the majority of our data is right here in the middle, that this is what we expect or what is likely to happen, as we talked about when we were doing standard deviation. And so when it says the second thing, so we completed our histogram, and so now what we're going to do is we're going to draw points here so that we can just get an idea of where these things are so that we can see them. And so what we're going to do in order to kind of show distribution, the way that we show distribution is we show that with a graph. And so the way that I create this graph is I take a curve and I connect all of these lines together, kind of like what we used to do with our functions in creating parabolas. But we notice that it kind of tapers at the end here, and it never actually crosses the x-axis. So one of the things that we can observe is that it doesn't cross x-axis. Another thing that we can observe is, again, there's symmetry, and we're going to say around the middle, which kind of answers that second question. And if we think about what the highest point is, when we kind of think about histograms, remember this is also kind of what we refer to as our median. This is counting frequency. So one of the things that we have to understand is that this is the frequency of a graph. So 5 happens the most frequent, 4 and 6 happen the next frequent, and so that we can say that 5 heads is the median. Now, if I was to kind of continue answering these and I was to ask you about what we know as the mean, median, and mode, so first of all, the middle is the median, so right there in the middle, this would be the median, because if you think about it, if something is symmetrical, the middle is going to be right on that line of symmetry. The mode, because its frequency is the one that occurs the most often, which is also in the middle. And if we have equal balance, so when we talk about the same number above is the same number below, when we talk about our average would also be somewhere here in the middle. So one of the things that we can kind of theorize, or one of the things that we can observe about this, is that they seem to all be the same. And so when we talk about mean, median, and mode, we can kind of refer to them in a scenario like this, that they are all the same. And we'll talk about that here on the next slide. And so what we can characterize is something that we refer to as normal distribution. So when we talk about normal distribution, anytime that we want things to be normal, things that are going to be the same. Now, these things do not happen very often. These are a lot of the times things that are theoretical in principle, but the idea is that when we want to try to describe things as being normal, things that are equally likely to happen, there are a few characteristics that go along with what we call a normal curve, or what is also known as a bell curve. The idea is that the mean, median, and mode are all the same. So when we saw examples before, we would typically talk about those examples of being normal distribution, where you have the same number above and the same number below, and they were equally spaced away from the average. It's a bell shape, and it's symmetrical around the mean, or again, this is going to be in the middle of our histogram, so it's symmetrical in the middle. It never touches the x-axis. One of the things that go with this is kind of like the asymptotes that we talked about. But the idea is that the reason that this doesn't exist is because we talk about probability, and that probability will never be nothing, or never be zero. So we will never have something that's 0% likely to happen. And what that goes along with is that the total area under the curve, so if we were to count all of that space that's under there, is equal to 1, because as I talked to you about before, that total probability is always going to be equal 1. It'll be 100% of all the potential opportunities to happen. And so the idea of what this is going to look like, what a normal curve looks like, is that first of all, we start off with everything that we've done before, and this is going to be some kind of number line. And on this number line, we're going to have a few things. You're going to have your average, you're going to have your median, and you're going to have your mode, all in the middle, and you'll see those as being the frequent. And so what happens is that you have this kind of bell shape, so it goes up, it peaks at the middle, and it comes down, and it's symmetrical. And so it never touches, because we don't want to say that something is going to be 0% likely to happen. But again, what we kind of show this as is we also show this as frequency. And so frequency goes on a range from 0 to 100%. Now typically you won't ever have that with a distribution, because obviously we saw that that middle value was not 100% of the information. It actually ended up only being about 24% of the total number of possible outcomes. But the idea is that all these normal distribution curves, this is what we call a normal curve, they all have this appearance. Mean, median, and mode are all equal. It's a bell shape, it's symmetrical, never touches the x-axis, it gets really close, but it just gets further and further away from the average, and it's all 100% probability that goes into it. Now the way that this works, and this is something that we're kind of going to talk about too as well, so we're just going to draw this a little bit again. So first of all, what we have is that we have more characteristics. So first of all, we have our number line. Here is our average in the middle. And so when we draw our curve, we have this bell curve. Now, the way of some of the things that we talked about before is that you have to understand is that we talked about standard deviation and how that plays with distribution and everything else like that. Now, standard deviation, as we talked about before, they are these boundaries that we use to kind of show how far something is away from the average. And so if you look at these things, a perfect bell curve, so in the perfect scenario, 68% of the data fall within one standard deviation. So what that means is if we were to track out standard deviation, which we kind of talked about before, changes every single time, it's not always the same for each data set, is that you would have the first standard deviation, so you would add that first standard deviation away from the mean, and then remember that it always goes in pairs, so we have this -1 over here. So all of this combined in here is 68% of the data. So this is 68%. So we talked about before when we were collecting our own data that we saw that the majority of our data was within that first standard deviation. But in a perfect situation where we had an equal number of parts above the average and below the average and they were spaced accordingly, we're going to get exactly 68% that kind of falls in this window right here. And so if this curve describes all of our data, most of it is going to be in that first standard deviation. Now what we're going to do is we're going to keep marking out these standard deviations. So we have 2 standard deviations away, because remember we take our average and we add and subtract standard deviations to keep going further and further away. And so we go to the other side, so we have -2. And so these two together, not separated, but these two together, the first 2 standard deviations, are going to have 95% of our data. So almost all of our data should be within 2 standard deviations. And this kind of goes along with the fact that we expect things to be a certain distance. There are certain expectations that we have for data, that if we have an average, it shouldn't be too far away. It shouldn't be too different from all the other values that are in there. And that if we start to get stuff that is more than 2 standard deviations, it's probably something that we consider an outlier and something that really shouldn't be happening. And so our last standard deviation that we'll see is that we have 3 standard deviations. And so all of this together, and I won't put that up there because it's currently here too as well, is 99.7% of the data. Now, this is what we're talking about where this line does not touch the x-axis, because we're saying that in a perfect situation we should be able to describe 99.7% of the data, but there's still going to be that 0.3 that we can't necessarily say is never going to happen, where there's something, as we use kind of sport examples, where someone might break a record or someone might fail miserably, and that's not something that typically would happen, but it's still something that we can observe. But when we talk about perfect situations where we have perfect data that follows certain patterns, these are the numbers that we're going to refer to back and forth. So we're showing these to you now, but then we're going to actually use these to kind of calculate probability of things happening and things not happening. Now, what we can also do is we can talk about things that are not perfect. We can talk about things that are not symmetrical, things that kind of have most of your data pushed to one side or the other, and this is something that we call skewed distribution. Now, skewed distribution can be skewed to the left, as you see, or it can be skewed to the right. And so what that means for us is it kind of looks like our graph, our bell curve, but just kind of a little bit more shifted to one side or the other. And so for skewed to the left, it kind of has this appearance, where the mountain is kind of just pushed to one side, and then skewed to the right, kind of the opposite would be happening, where all your information would be skewed kind of over in this way. Now, the reason that we talked about left skew versus right skew is I know that it seems a little bit backwards from what we're seeing, but you'll kind of see what I mean by this when we start to introduce the fact that this one right here, this is going to be our mode. So the mode goes with the highest kind of peak there. Then we talk about the middle of the data kind of gets skewed over to the left side. So the median isn't really in the middle anymore, it's just kind of skewed over to the left. And then if we talk about our average gets pushed even further, because we start to expect things that shouldn't be necessarily where they are. They should be kind of different from what it really is supposed to be, and it doesn't really give credit to what our values really should be. And then the reason that it's skewed to the left is because these numbers that are down here, these kind of infrequent numbers, kind of these outliers, if you will, that aren't typical data, which would be over here, those are dragging the average lower and lower and lower, kind of to the left and more to the left. Now, as far as kind of skewing this to the right, kind of the same thing happens. Here is going to be our mode, still where it normally should be, right at the peak of that graph. But again, our median gets pulled a little bit this way because we still have to figure out what is in the middle. It's not as pulled as far as the average because we talked about median isn't as affected by the average, but these values that are populated over here are dragging our average closer and closer so that we can make sure that everything fits. But this is kind of most of the things that we're going to run into is non-typical, non-normal data, skewed data, where all these values are not the same. But that's why we try to normalize all our data. That's why we try to collect as much data as possible, because the more data that we collect, the more likely it is going to be more normal so that we get the mean, median, and mode being as close together as possible. So now what we're going to do is we're going to kind of look at some examples of normal distribution and how we can use calculation to show what it is that we're looking for. Okay, so here we have a table of heights of 4th grade students, and the idea is that we're given the frequency, so how often that occurs. So for example, if you look at the first entry in the table, which I believe you need to copy down, is that you have 130 centimeters happens twice, and you can go through there and it shows you how many students would be that particular height. And so if we look at our histogram, the idea is that we want to create a scale. We want to create something so that we can kind of look at the fact of, hey, we have all of these heights that are kind of distributed around here, and we want to look at what they are going to be so that we can kind of look at their distribution. So I'm just going to go ahead and I'm going to label this graph with the different heights here, and we're just going to show you how we can construct a histogram given information that we have. So I marked out a bunch of our little spaces here. And so just like we did with the other thing is we're just going to create these boxes rather than just these X's. So 130 happens 2 times. So if you look at my scale here, roughly we're talking about here being 2, which isn't all that spectacular. The next one is 7, so we just have these two things, they're going to be joined together, so one is going to happen right after the other, so we're kind of boxing it over. Notice that I'm not starting in the middle of the tick mark, I'm kind of hovering over top of it here. Then I go with 9, and then I'm going to go with 20 would be the next one, so 133, there's 20, so I'm going to take my line up to 20. 134 is going to go all the way up to 38, so pretty much to the top. If we go to the next one, we have 18, so it's a little bit less than the other one on the other side. Then we go to 12, so it's a little bit more. And then we go to 10 exactly, so that's pretty close. And then we go to 138, which is at 5. So if we look at this, this isn't perfect normal distribution because there's no symmetry here because the values are a little bit different. But if I was to draw a line through these, you could see that this obviously has some sort of bell curve and that it gives the appearance of somewhat of a normal distribution. Now from this information we can kind of talk about our standard deviations, and we can talk about all of this stuff that we have going on. So let's answer a couple questions based on this information. So first of all, it says what percentage of the students is shorter than 135 centimeters? Now this is something that we can do talking about just probability in itself. So if we talk about all the students that are shorter than 135 centimeters, it's all these students from 134 below. So if we wanted to, what we could do is we could just go ahead and add those together, and so we have 20, 50, 60, 76. So we have 76 out of the 121 students. And so if I went ahead and I did that division, I would get an answer of about 63% of the students that are there. Now, the idea is that we're just using this information, so we're looking at these typical heights. Now, when you think about heights of children, the idea is that you should have just as many people that are taller as the number of people that are shorter. And so question 3 is, what is the probability of the height of a randomly selected student would be greater than 132 but less than 138? So again, we're going to look for what those values are. So greater than, so we're going to look at greater than. So everything from 133 all the way to 137, that would be the range, because we want it greater than 132 or less than 138. So again, we're going to add those values together, and we're going to get a value of 98 out of that 121 students. And so if we do that division and get a decimal for our answer, we would look at 81% of the students would be in that kind of general vicinity. So not always do we need to look at things being perfect. Not everything do we need to look at everything being normal, but we can look at this information and we can just describe and we can talk about what it looks like and how it acts, and the way that the information is laid out for us so that we can make decisions based on information. For those of you that have been to Cedar Point, sometimes height requirements are a big deal. You want to figure out, if I'm going to take my 4th grade students, are a lot of them going to be able to go on the rise that they want to, or do I need to wait until more of my students may hit those requirements, or something like that. So we want to just be able to lay out this information, create the histograms, count up the frequencies, because that's really what it's about. You're counting up frequencies and you're making fractions out of them based on the total number that you have there. This is what we call sampling, and we're going to talk about that later. But the idea behind it is that this is normal distribution. This is things that are normal, things that are slightly normal. Maybe it's skewed, maybe it's not skewed, but we're looking at it in terms of how can we use this information to help us out. Now, as we continue with this information, so it says how many 4th grade students are represented in the data. We already counted those up because that was the total frequency. So I'm just going to say total frequency, and that was 121 students. Now it's going to ask me what is the mean height of the data set. Now, question 5 and question 6 kind of go hand in hand. It says, does the data appear to be normally distributed? And I would say yes, there is slight symmetry. The mean, median, and mode seem to all be the same, and so basically for us, our information is that our average would be the same as the median. Our average would be the same as the mode, which was the middle, in our case, was 134 centimeters. That appeared to be the mean. That appears to be the mode. That appears to be the median, because all of those in normal distribution. If we say 6 is normal distribution, or question number 6 says that it is normal distribution, the idea is that that would mean that the mean, median, and mode would all be the same, because we're expecting them to kind of work that way. Now, there is a way that you could do that. You could actually list out every single 121 of those students, and you could put that into a calculator, and you could have it crank out the average for you, and you would probably see that it would be very close to 134, just because of the appearance of it being normally distributed. Okay, so now we're going to look at some of the same idea of looking at normal distribution and kind of the decisions that we can make. So as you see here, we have graphs that below the number of pets veterinarians own, and the value associated with those is a fraction with how many pets they are. So if I look at this, a couple of things that stand out to you, or should stand out to you, is that all these fractions have a denominator of 400. That means that they've surveyed 400 different veterinarians and asked them how many pets do they own. Now, you would think, if you were asking that question, or you were trying to get an answer to that question, that the idea is that you would think, if someone is a veterinarian, then they probably have a lot of pets at home, or they have a lot of pets, at their place of business, or, they just enjoy being around pets, so they're going to have some of their own personal pets that they have, no matter what those are. And so if you look, we get varied responses from 0 to 10. Now, think about this. You have a veterinarian, you had 2 veterinarians here that answered your survey saying that they had 0 pets. And so you have a couple of veterinarians that are like, hey, I don't have any pets. You might think that's weird, because you would think, hey, you deal with pets, why wouldn't you have one? Well, you don't know the answer to that question. Maybe they're just busy. You can look at 10 here as being a similar situation. Obviously, you probably don't have veterinarians that have an obscene amount of pets. I mean, over 10 pets, that's just kind of a large amount of pets. It kind of depends. You'd have to spend a lot of time taking care of all those. But if you look at the bulk of our information, the bulk of our information kind of lies in that 3 to 7, 4 to 6 range, where you have kind of a normal amount of pets than what most people have. And so what 2 questions that we're going to ask is just how we use these histograms is that says shade the bars representing owning more than or equal to 5 pets, and what fraction of owners have 5 or more pets. So we're basically saying, okay, what number of veterinarians, or how could I explain the general population of veterinarians and how many pets they own? And so we're going to do 5 or more. So we're going to shade everything that's 5 and greater than that. So all we're going to do now is we're just going to count these values up. And so we want to make a fraction out of this. So we have 90 plus 70 plus 52 plus 25 plus 3 plus 1. And so of the people that we surveyed, of those 400 veterinarians that have had more than or equal to 5 pets, we would say, or we could say in general, that 241 veterinarians out of 400, if I do that division real quick, you would see that that's 60%. And so I could make a statement that says, hey, 60% of veterinarians have a lot of pets. I would consider 5 or more to be a lot of pets, so why wouldn't I say, hey, this is the number of people that responded to my survey and said, hey, this is how many pets that I have. Well, that's 60% of my veterinarians. Now, we can do that with some other stuff, so we can kind of look at specific questions that we're trying to look at. So owning more than 2 but fewer than 7. So if I was to shade that in, that would be this general area here. So more than 2 but less than 7. So we're not going to include those ones. And so again, we have our values that we can add together. So we have 51 plus 71 plus 90 plus 70. And if I add those up real quick, making sure that I get the correct number, we have 282 out of the 400. So again, I'm still using that 400 because that's the total number of people that I've asked this question to. And if I do that division there, divide by 400, I get about 70.5% of veterinarians have between 3 or more than 2 but less than 7. And so we're just kind of looking at general assumptions that we can make about data, how we use histograms to count frequency, to kind of make generalizations. So the idea is that show histograms, show these fractions, show these probabilities, as we would call them, about how likely it is for something to happen or for something to not happen, but keeping in mind that it all has to equal 100%, or the amount over the same amount. So in this case it would be 400 over 400, which equals 1. So the idea here is that we're looking at normal distribution, how standard deviation has a play in normal distribution, and we'll talk about this a little bit more too as well. So really all that we're doing today is we're looking at this information, so make sure you have all this down, make sure you have this all copied, and we'll be good to go for tomorrow.